Is it visible now? Okay. So in the last class, we actually considered what are the field components of the TE wave propagating in a rectangular waveguide. And we noted that there are some 6 components were there. Since Ez is 0, we are left out with only 5 components. And in the solutions, what we have written earlier, like Ex, Ey, Ez, etc., we are having cos and sine functions, which are having arguments with m pi x by a, n pi y by b. M and n are some numbers, and whatever the other things like b is the breadth, a is the width of the waveguide, and x and y corresponds to the direction in which the field components are represented. And one of the important thing in waveguide system is nothing but modes. So what are modes in a waveguide system? Modes are nothing but regular field patterns corresponding to electric and magnetic waves. So they are nothing but field patterns of electric and magnetic fields that are present in the system. So in order to represent the modes of a given TE wave, generally we use the representation TE of n suffix m comma n, where m represent field variation along the x direction, n represent field variation along the y direction. So m represents field variation along x direction, n represents field variation along y direction. That means the value of m will determine the order of the mode. So m and n values can be 0, 1, 2, 3, etc. And these represent order of the mode. Whether it is lower order mode, higher order mode. Starting from 0, we can have different values like 1, 2, 3, etc. Higher the values, we call it as higher order mode. Lower the values, we call it as lower order mode. And one important thing is, if you look into the equations of the field, what we have represented, since they involve sine and cos functions, if both m and n are 0, all the field components will be 0. No field component will be present in the waveguide system. So this results in a wave that is not at all propagating in the waveguide system, and hence m is equal to n equals 0 is not possible in a waveguide. Other combinations like m equals 1, n equals 0, m equals 0, n equals 1, like that different combinations are possible because at least few components will be non-zero. So that can be written in this form. If m equals n equals 0, all field components are 0. If you substitute m equals n equals 0 in the equations of Ex, Ey, Hx, Hy, Hz, all of them will vanish because they are functions of sine and cos functions. Once there is a cos function is there, so it will be 1, but sine function will vanish. So that product function will be, resultant will be 0. So this is not possible. So this is not possible. Hence, we can have combinations like TE10, TE01, TE12, TE21, etc. Different combinations. M equals 1, N equals 0, M equals 0, N equals 1, and similarly M equals 1, N equals 2, etc. So other than M equals N equals 0, we can have other field components in the waveguide system. And the field pattern can be written in this form. Say for TE10, I can write the field pattern in this form. So this is your A, this is your B. The electric field will be along B. Magnetic field will be in the form of circular loops. So this is H field, this is E field. If we take the cross section of the waveguide, the electric and magnetic field will be in this form, such that if you see the side view of the waveguide system, so electric field will be in the form of circular loops. Like this. But connectivity is not possible inside the system. This is E field. If you write the H field, it will be in the form of a circular loop. So H field will be, if you consider this as the waveguide, it will be in the form of circular loops. So they will be either in this form, so it will be in circular loops. What I have written. So it will be either in any direction that is actually possible. So this is H field. And regarding that M and N, what they generally say that, which are called as the modal numbers, which determines the order of the mode that is supported by the waveguide system. Some of the textbooks says that it corresponds to the number of maximum values that occurs across the cross section of the waveguide. Some textbook says that it corresponds to number of zero crossings that occurs for the field across the cross section of the waveguide. Both way it is one and the same. Whether you take number of zero crossings or number of maximums or peak value of the fields, whether it is E field or H field, it is one and the same. So M and N are called as the modal numbers. So M and N are called modal numbers. So they represent number of maximums or number of minimums of field across the cross section. M equals 0 means no peak, no zero crossings. N equals 1, 1 peak or 1 zero crossing. M equals 1, N equals 1 means there will be one zero crossing, one peak. Like that, they tell about what is the orientation of electric and magnetic field along the cross section, across the cross section of the waveguide system. And here we come across an important terminology called as the dominant mode. What is this dominant mode? Suppose if we consider a waveguide, waveguide is generally operated in a frequency range. I mentioned that the microwave frequency that is ranging from around 1 gigahertz to 300 gigahertz is divided into a number of frequency bands. C band, S band, L band, K band, KU band, KA band, like that. Each of the frequency groups are designated with some terminologies according to IEEE. Earlier we were having ITU, International Telecommunication Union standards, but after the advent of IEEE, they redefined the frequency ranges corresponding to these bands. So bands name will remain same, but only thing is frequency of the groups will be little bit different. So waveguide is operated in a frequency range. Like F is between F1 and F2. F1 can be 1 gigahertz, F2 can be 10 gigahertz. F1 can be 10 gigahertz, F2 can be 30 gigahertz. C band, S band, L band next, 30 gigahertz, 100 gigahertz. Like that, there will be a frequency range over which a waveguide will be operated. This we call it as lower threshold. This we call it as higher threshold. There are two frequencies corresponding to the frequency range. One is called as the lower threshold frequency, higher threshold frequency. Or we can call this as minimum frequency. This is called as the maximum frequency. Therefore, dominant mode is nothing but the mode corresponding to a frequency in the waveguide which corresponds to the least value supported by the waveguide. Because if you say that the frequency of operation is between say F1 and F2 for a waveguide system like C band, S band, etc., what is the least value of this frequency? So least value of frequency in other domains, we can call it as longest wavelength. Least big frequency supported by the waveguide, or the longest wavelength supported by the waveguide corresponding to a field pattern is called as the dominant mode. So if you are having a frequency of 1 gigahertz to 10 gigahertz, 1 gigahertz is the lowest frequency for that particular band. So that it corresponds to the longest wavelength supported by the waveguide. Similarly, if we consider 10 gigahertz and 30 gigahertz, so 10 gigahertz will be the least frequency, which corresponds to longest wavelength. So lower threshold of the frequencies is generally considered as the dominant mode frequency of the waveguide system. So we can write here smallest frequency supported by a waveguide, or longest wavelength supported by the waveguide, since F is inversely proportional to lambda. Lambda is C by F, or F is C by lambda, if you write it in equation form. So what is the smallest frequency supported by the waveguide? Correspondingly, what is the longest wavelength supported by the waveguide is generally called as the dominant mode frequency of a waveguide system. And corresponding to the waveguide system, generally your waveguide will act as a high pass filter that we are going to prove later when we consider the waveguide parameters. Waveguide act as a high pass filter means if you write the response, it will be in this form, ideal form. It has a cutoff frequency. That means waveguide is to be operated above certain frequency only. Below this, the waveguide cannot be operated. So, since this is the least frequency supported by the waveguide, the wavelength maximum supported will be nothing but C by Fc. Fc is nothing but the cutoff wavelength, cutoff frequency. C is nothing but velocity of light. Lambda maximum is nothing but maximum wavelength supported by the waveguide. So this frequency mode is called as the dominant mode. So smallest frequency supported by a waveguide or longest wavelength supported by a waveguide is called as the dominant mode. So then the question arises that why we should excite this dominant mode inside the waveguide system. So whenever you want to transmit a TEM wave or TE wave inside the waveguide system, TEM wave is not possible. TE or TM wave, we have to use a source. A source will be generally used to excite the different modes in the waveguide system so that the modes will get propagated by multiple reflection inside the waveguide system. So then what are the reasons or what are the advantages we get? Suppose if we excite a dominant mode inside the waveguide system. So we can list them. So advantages of dominant mode. So we have already defined dominant mode. Once again I will tell, dominant mode is the frequency inside the waveguide corresponding to a mode such that the frequency is minimum or it is conversely corresponding to longest wavelength. In other words, we can say that minimum frequency supported or longest wavelength supported by a waveguide. That we generally call it as the guide wavelength. So sorry, this dominant mode of a waveguide system. So what are the reasons for which we are to support the dominant mode? One important thing is, since waveguide is used as a communicating medium to transfer power from transmitter to antenna or an antenna to a receiver, as I have mentioned earlier. So naturally we want to see that there should be maximum power transfer. So no losses must be present. So if you excite a dominant mode, maximum power transfer possible. If you support other modes, it is not possible. Only with dominant mode, it is possible to transfer maximum power from source to destination. Source can be transmitter, destination can be an antenna. In other case, source can be an antenna, destination can be a receiver. So like that, it will result in maximum power transfer. And another important thing is there will be minimum losses. We have already mentioned what are the losses in the waveguide system. One is called as the reflection loss. Another may be what we call it as the scattering loss. That may be very small in the system. And another thing is dissipation loss. Because it is made up of conductor, when current flows, there may be some loss will be present. So these losses will be minimum in the waveguide system if we are able to transmit the dominant mode. Another thing is this mode can be easily generated. For each of the mode excitation, we have to use a combination of waveguide system or transmission lines and an antenna that is generally used for exciting these waveguides, this modal pattern inside the waveguide system. By attaching this antenna, small antenna, and the transmission line or waveguide section to the wall of the waveguide. So the arrangement what we use for exciting the dominant mode is very, very simple. So this mode, hence your exciting of the dominant mode is very, very easy. That is one more important thing is. Next thing is dominant mode will have mode symmetry. So mode symmetry is very important in long distance communication. Long distance means like base station to transmitter of the satellite system or transmitter to a transmitting antenna which may be outside the building. Like that, in long distance communication, what happens? Your modal pattern should remain same. If modal pattern changes because of the various things that comes into picture, it may be due to dielectric constants variation or dimensional variation and other what is called as the imperfections that comes into picture. So there will be a problem called as mode slipping. So a given mode will be converted into other mode. So that will result in losses, because always we have to see that at every point in the communication link, your mode should sustain or it should be same as it was generated at the transmitting end. So mode symmetry will result in long distance communication, so without losses. So mode symmetry will prevent mode slipping. Slipping of modes is prevented, so which reduces the losses. Otherwise, there will be appreciable losses if a dominant mode is converted into other mode or something like that, or one mode is converted into another mode, etc. So mode slipping can be prevented because of mode symmetry. Even if there is slipping is there, so same pattern will exist. Whether you take horizontal direction or whether you take vertical direction, any direction, the pattern will remain same, whether it is slipped or not slipped inside the waveguide system. That is one more important thing. So with regard to these 3 or 4 important points, we say that TE10 is the dominant mode in rectangular waveguide. Similarly, if you consider TM wave, TM11 is called as the dominant mode in rectangular waveguide. So TE10 is called as the dominant mode. TM11 is called as the dominant mode in a rectangular waveguide system. So first we stated that what is meant by a mode, what will be the advantage of exciting dominant mode, which is the dominant mode in a rectangular waveguide system. And apart from this dominant mode, one more terminology is generally considered, which we call it as degenerative modes. Degenerative modes. What is meant by degenerating modes? If we take an example, say TE12, this results in a pattern. inside the waveguide system, as we have mentioned about TE10 already. Suppose if there is mode slipping, this modal pattern may be converted into TE21. That means M value changes from 1 to 2, N value changes from 2 to 1. This we call it as mode slipping. Mode slipping occurs because of different things. That means during the propagation, there may be discontinuity in the path. There are reasons for that one, we can say that. So discontinuity in path, one reason. Second reason, dielectric constant variation. If it is not uniform, if it varies, then also there is problem. Another thing is dimensional variation. Because we have stated width should be A, breadth should be B. There may be micro variations in the dimension because of what is called as fabrication problems. If the waveguides are not properly fabricated, there may be small variations in the width as well as the length. So that will cause a micro variation in dimensional thing, so that also causes this mode slipping. So mode slipping or degenerative modes is nothing but conversion of one mode to another with the same pattern. TE12 and TE21 are the symmetrical modes, so that we can have in this particular form. Similarly, TE13, TE31, TE4114, like that, different combinations. So this will result in loss of signal. All these things will result in signal loss. Even though the field components and other things come out to be same for the shifted mode, but generally the pattern has to remain same for a given type of frequency and given type of modal operation in the waveguide system. So first thing is, what are the modes? What are the advantages of dominant mode? Which are the dominant mode? And what is meant by degenerative mode or mode slip? And the analysis what we have done so far is for TE waves, that is transverse electric waves. The same analysis can be done for TM waves also. So next thing is TM waves. These are also called as E waves, where Z is equal to 0, Ez is not equal to 0. So no magnetic component along the direction of propagation, but there will be an electric component along the direction of propagation. Ez is not equal to 0, but Hz is equal to 0. TM waves. So same method what we have done for TE waves, starting with the Maxwell's curl equation, using the wave equation, using appropriate boundary condition, using separable of variables with product solution, etc. We can write what are the field components. So if you want any derivations, you can refer to any textbooks. So cross, field theory by Cross and Carver, and same title, antennas and the microwave system by Cross and Carver. In that also he has discussed about the waveguide system. So he has given detail about how to find the solution by product solution method and separation of variables. So in the same way, we can do that here also. So field components, TM waves, field components, same method as in TE waves. So use Maxwell's curl equations and wave equations. Next, appropriate boundary conditions. Like E tangential, H normal equals 0. Product solution, assume product solution, use separation of variables. If we use these methods, we will get the field components almost ideal or similar to that of TE field components. We have already written some 6 components. On the same way, we can write what are the field components for TM wave. So, if you write the electric field components, E of x is equal to E naught of x, magnitude, cos of m pi x by a, sine of n pi y by b, into e to the power of minus j beta z, into e to the power of j omega t. Those things I won't write because it is implicit. I mentioned that field not only varies with respect to distance, it also varies with respect to the time. Both of them are to be incorporated. With respect to distance, whenever wave has to propagate, alpha should be 0, beta is non-zero, so that your exponential function only contains the phase constant among the in the propagation constant of the waveguide system. And next important field component is EY. It is almost similar to this one, so but it involves sine cos functions. Sine cos function, same thing, e to the power of minus j beta zt, z, and e to the power of j omega t, multiplication factors. It is one and the same. Next thing is Ez. Ez is E naught z, so it will be sine function. Same thing. So coming into Hx, H naught of x is the amplitude. Then it will be sine cos function. Sine n pi x by a, cos of n pi y by b. Hy is equal to H naught of y. So it will be cos sine function. And finally, Hz is equal to 0. That we have already mentioned. Ez is non-zero. Hz is 0 for TM waves. This is also called as E waves. As we have already mentioned that TM11 is the dominant mode. The field pattern for that can, it will be in this form. So one is electric field, this will be magnetic field. If you consider the magnetic field, the side view, it will be in form of circular loops. Like this. Like this. Center. in the form of circular loop at the end. So this is HP. So getting the field components for TM wave is one and the same. Only thing is, instead of using a wave equation delta square is equal to 0, here we use delta square head side is equal to 0. Instead of delta crossing, we consider delta z as the curly equation. But del cross E is also used. We must have at least 6 auxiliary equation to find 5 components of the electric and magnetic as mentioned earlier. So next thing is what is called as the circular waveguide system. Circular waveguide example is optical fiber. So optical fiber is also a circular waveguide. So cylindrical coordinate system are to be used for solving the field components. Maxwell's curly equation corresponding to del cross E and del cross to be used. But Laplacian operator del square will be different for cylindrical coordinate system or your circular coordinate system. R5Z is used. And again, using same separation of variable method with product solution, assuming the boundary condition, we can find what are the different field components of the waveguide system. So possibly I will take that one in the next class because I got there. I had to write so many equations.